So today we are going to be talking about chapters 1 and 2 of general chemistry. If you're new here, hello, I make one-page mind maps to simplify MCAT topics by condensing chapters into visuals that make sense to me. I'm currently studying for the MCAT, and I think that this has been very helpful for me in seeing how concepts connect. It's also nice to have a one-page summary of the chapter that I read. Often 4 to 6 pages of notes can take time in reviewing, and it's been helpful for me, so that's why I'm sharing it. Okay, so disclaimer, I have been getting comments about how the maps are very complicated. They are complicated. It's because they're meant to be. If you have 30 pages of a chapter, it's going to be really hard to condense that chapter into one page without that page not looking completely full. Right? And so this works really well for me because when I was in undergrad, I would make formula sheets like this and review them before exams. But this might not work for everybody. Maybe you need to have 3 or 4 pages where you separate different concepts to help you learn and understand better. But if you are looking for a one-page sort of summary, then this might work for you, okay? So let me know if this works for you. And also, what do you do to summarize chapters? Do you also make notes like this? What do you do? Okay, so this video is a part of my MCAT Mind Mastery series on my Substack where I'm documenting my MCAT study journey. If you're interested in that, you can follow me on Substack. I will put the link below this video. We're going to start a discussion by talking about the atom. So here I've labeled the parts of the atom. The nucleus, of course, has protons and neutrons. Protons are positively charged and 1 atomic mass unit, or 1.6 times 10 to the negative 19 coulombs. Remember that a coulomb is just the charge per unit time. Neutrons are neutral. They are about 1 atomic mass unit. The number of protons of an element, as you can see, this is the periodic table, is the atomic number of that element. It's the ID of that element. Lithium, for example, has 3 protons, and that's the atomic number of lithium as well. Something I also boxed here is that neutrons plus protons is equal to the mass number of the element, or the atomic mass of that element. Have the electrons in their shells. So electrons, they're negatively charged. They are basically negative 1.6 times 10 to the negative 19 coulombs. The outermost shell of the atom has the valence electrons, right, which can help in bonding and things like that. So around this drawing of the atom, I also included sort of how the idea of the atom actually evolved. So initially there was a person who actually proposed that the atoms are solid spheres. Rutherford, who I included here, this is how he looks, used the gold foil experiment shooting alpha particles at thin gold foil. He saw that most went straight through, but some deflected, meaning that the atom has a dense positive nucleus surrounding mostly empty space, and that's sort of where this idea came from, right? Then came Bohr, who refined this idea with his planetary model, saying that electrons orbit the nucleus in specific energy levels or shells. When electrons, they jump between energy levels or shells, they absorb or emit discrete amounts of energy, and that's what gives us atomic emission spectra. So this is the basis of the emission spectra. Essentially, when the electron moves up and down energy levels, that causes the electron to release different wavelengths of radiation, and those wavelengths are seen by us as colors or colored light. Then we have Planck. Planck said that the energy that is released as electromagnetic radiation is in packages called quanta. The energy of the photon is equal to Planck's constant, which is this, times the frequency. Frequency can be written like this and also like this. We can relate the speed of light equation to this energy equation and get this equation right here, because the speed of light is equal to the wavelength times the frequency. So then we can essentially substitute in for the frequency right here and get this equation. I just wrote out all of the equations and I sort of boxed them so that later when I'm reviewing this sheet, I can quickly see like what are the relevant equations here, how are they related to the topic as a whole. The other thing I included in this section is atomic weight. So as you know, atomic weight is the gram formula mass, the average of all of the naturally occurring isotopes of an element. It is different from atomic mass. Growing up, this idea always confused me, so I just put it here as well. Electrons, we discovered later, aren't little planets orbiting neatly. Instead, they exist in orbitals. which are regions of space with high probability of finding an electron. So this brings us to the quantum numbers, which I listed right here, which describe the location and behavior of electrons. The principal quantum number, n, shows the energy level or the shell. The azimuthal describes the subshell, s, p, d, f, and these are the numbers that correspond to each of those. And then the magnetic number is the orientation of the orbital in space. The magnetic number can be between negative L and L. So if L is 1, the range for ML will be negative 1 to positive 1. There's also the spin number, which can be positive 1/2 if the electron is spin up and negative 1/2 if the electron is spin down. Essentially, like I said, I wrote here as well, electrons exist in units of space called orbitals. Each energy level has access to different orbitals. These are the orbitals we're talking about. And each orbital has suborbitals or subshells. And each of those shells, they carry 2 electrons. You can actually determine exactly which electron you're talking about in the electron configuration of an element. Unpaired electrons are referred to as paramagnetic. Paired electrons are referred to as diamagnetic. Remember that unpaired electrons can form bonds. Pauli's principle is that no 2 electrons can have the same set of 4 quantum numbers. Therefore, the orbital can only hold a max of 2 electrons, right? And Hund's rule says that when filling orbitals of the same energy, electrons first fill them singly with parallel spins. So when you start filling these orbitals, you have to fill them up singly before you go back and add more electrons. The last thing I want to talk about here is the Aufbau principle. It states that the electrons fill orbitals starting from lowest energy levels to higher ones. By knowing what each quantum number means, you can then write the 4 quantum numbers for a given electron. Okay, so now that I have the electron configuration, I can then determine, okay, how does this actually look like? So essentially, this is what it looks like. This is 1s, this is 2s, and this is 2p. Now, if I go in and draw the electrons, I'll write 1s2, 2s2, and 2p2. So now if I ask myself, hey, can you give me the 4 quantum numbers for this electron right here? I would do it like this. N equals 2, because we are in the second energy level. L equals, we're in P, so L would equal 1, because P is 1. ML, therefore, would be negative 1 through 1. In this case, since we're right here, it would be 0. So ML would be 0 because this is negative 1, this is 0, and this is 1. MS would be spin up, so positive 1/2. And these are the 4 quantum numbers. So as you can see, by knowing what these 4 quantum numbers mean, I can then go and determine the 4 numbers for this electron right here. Essentially, quantum numbers help us describe the location and the behavior of electrons as best as we can. So now let's talk about the trends going across the periodic table. So first, I'm going to be talking about ionization energy. So ionization energy is essentially how tightly electrons are being held. I'd like to know what these terms actually mean before telling you about the trend. So ionization energy is how tightly electrons are being held. Okay, for example, this is lithium, this is francium. Francium, as you can see, has way more energy levels than lithium. So francium's valence electron right here is incredibly loosely held. So the ionization energy is low because the electron is so far removed from the nucleus, it can't feel much of that attractive charge. In contrast, lithium has a higher ionization energy because its electron is much closer to the nucleus, it's more tightly held. Ionization energy increases as you move up and to the right. It takes more energy to remove an electron from smaller, more positively charged atoms. The other thing I want to tell you is if you have a stable ion that you've ionized, being able to remove more electrons is very difficult. For example, so magnesium sits right here on the periodic table. As you can see, magnesium can give away 2 of its electrons because that will make it stable, right? So we give away 1 electron, this is how much energy we spend. We give another electron away, and this is how much energy we spend. After that point, magnesium, like I said, is now stable. It has the same configuration as, say, neon, right? which is a noble gas. Noble gases are very stable. If we try to remove another electron, as you can see, look at the energy jump here. So removing more electrons from a already stable ion requires a lot of ionization energy. Okay, so now let's talk about atomic radius. So as you know, elements with a higher number of energy levels, right, they have a higher atomic radius, right? They are very big, like francium. However, increasing the proton number across the table does not increase the atomic radius, because at that point you have more protons, more positive charge that pulls those electrons inward, so it decreases atomic radius. So the trend for atomic radius is that it decreases as you go right, because more protons pull electrons inward, and increases as you go down, because there are more shells, so you have a larger atom. Now let's talk about electronegativity and electron affinity. Both of these increase toward the top right. Electron affinity is the amount of energy released upon electron uptake and reception. It's greatest in things that want the electron, as in things that are close to being noble gases. In contrast, electronegativity is the relative attractive force that an atom exerts on an electron within a chemical bond, and it's based on the CH bond. The CH bond was found to have an electronegativity difference of 0.4. And based on that, we can say that a covalent bond has this electronegativity difference, and an ionic bond has this electronegativity difference. For this, I also want you to note that metals, so these are all of your metals, right? You have your alkali metals, alkaline earth metals, transition metals. These, of course, are metalloids, and these are nonmetals. But your metals, they lose electrons easily because they're electropositive. Nonmetals, here that we talked about, they tend to gain electrons, okay? These trends all tie back to the effective nuclear charge, essentially how tightly the nucleus holds onto electrons. The thing we're answering through all these trends is what happens to the valence electron. Is it loosely held? Is it tightly held? And why? Now let's talk about the last two trends, which are the effective nuclear charge and the ionic radius. So the effective nuclear charge is the charge felt by the valence electrons, and essentially it's just the number of protons of the element minus the number of core electrons. So the more core electrons you have, the less charge your valence electrons are going to be feeling by the nucleus. Because the core electrons, they protect the valence electrons from the influence of the nucleus. So this is how you can calculate the effective nuclear charge. Now, lastly, we're going to be talking about ionic radius. Ionic radius is different from atomic radius. Now we're talking about ions. So what happens when you take away an electron from sodium? Well, sodium now has this configuration. Magnesium has the same configuration when you take away its 2 electrons. And those are its valence electrons. So when you take away these valence electrons from these elements, you'll note that they both have the same electron configuration. Now the question is, do they have the same ionic radius? No, because magnesium has more protons than sodium. And what do those protons do? They pull in those electrons. So magnesium's ionic radius is smaller than sodium's ionic radius. You can observe that if they're pulling on the same amount of space, ion that has the more protons has a smaller ionic radius. This is the trend for ionic radius. Okay, so this is the walkthrough of my atomic structure and periodic trends mind map for the MCAT. If you think that I've missed anything here, please let me know. I would love your help. We essentially went from early atomic models all the way to how the periodic table organizes electron behavior and energy. If you found this helpful, like I said, you can follow my Substack, and let's keep studying together.